Okay, let's get on with this. The last, but not at all the least, Ravi Vakil is going to talk about drawing curves in space through a bunch of points. Ravi got his PhD at Harvard under Joe Harris, was an instructor at Princeton, is now a professor at Stanford, and not least is the president-elect of the American Math Society, where we are. He's written or edited 7 books, some for college students. The reviewer of one said the title of the book could have been, "Yes, Virginia, Math is Beautiful." So I like that title. And I don't think it's been used, actually, so maybe we could have a new book with that title. He's won awards for teaching. He's won many awards, Sloan Fellowships, AMS Centennial Fellowship, Career Grant, much decorated and much deserving of those honors. This lecture, by the way, is supported by an outside fund. Being a former fundraiser, I appreciate these things particularly. It's generously supported. I've never heard of an ungenerously supported lecture. By the Bose, Datta, Mukhopadhyay and Sarkar Fund, established to bring appreciation for mathematics to a broader audience. I guess you're the broader audience in this case, and I think we'll all appreciate this theorem after Ravi tells us about it. Ravi.
Great, thank you very much. Thank you very much, David. And so I'd also like to thank the organizers for inviting me here. I'd like to I realize the people who made this possible, including the donors who are undoubtedly not here, so it's good to appreciate them while they're not here, because then I can say that it's really great that they make it possible for to encourage things to happen that might not otherwise happen. So I think that's awfully cool. Yeah, let's clap for them. They're not here, and I think that they deserve clapping. And I also want to thank you for coming at the end of a long and exhilarating but still tiring conference. And what I want to do in this talk, over the course of the week, I met a highly non-trivial number of undergraduates, which is like kind of more than I even expected by chance. And so I really I think it's great that that number of them are at the conference. And I have no idea if they're in the room, but my intent is to make this something which is for everyone, for all mathematicians, including undergraduates. So I will, which does mean that, like any math talk, I fully expect to lose people inadvertently and advertently, but at least I want something with people. I want to try to carry people through as much as possible, much as the other speakers do. And I wanted to thank the other speakers for giving great talks, but unfortunately they gave really great talks, so I feel I don't want to thank them because they put me in kind of a difficult position. So my goal is to really tell you what I think is a great mathematical story, and like many things in mathematics, it appears to be about one thing, but secretly I want it to be about something bigger. So I want to tell you about this interpolation problem and tell you about some of the best ideas in its long history, which connect to lots of mathematical themes, and then to give you a glimpse, but really only just a general impression of some of the ideas that Eric Larson and Isabel Vogt used to finally bring this problem to a complete conclusion and have a complete answer to what the question is. So what I want to do is, for much of the time, is to discuss what the question is about, but in the course of doing it, we end up seeing lots of mathematical ideas that are real useful. And I did notice that a lot of the ideas I want to introduce were separately introduced in talks earlier this afternoon, which I absolutely am not assuming that you've seen, but I just think that's a sign of somehow the unity of all mathematics. Okay, so first I should say that there are some great newish ideas, newish meaning the last couple of years ideas, and they're all due to Eric Larson and Isabel Vogt for Brown University. And one of the many things I like about the story is it brings together different themes. So Eric and Isabel they're married. I'm married too. but they're married to each other. So like the nice thing is, and the fact that they work together on this as well, they're really, maybe from farther afield, they look like they're similar sorts of mathematicians, but I think that as they look at math, they have really quite different strengths. And so it's the combination of their different styles of mathematics that made the solution actually work, really come together. And so that makes this story, makes the mathematics that comes out of it that much more pleasant. Okay, so let me tell you what the problem is, at least vaguely. So here I have 5 points on the plane, and the question is in this case, n is 5, can I string a curve through them? And if I say this really vaguely, well, of course, it's easy to draw a squiggle through them. So what do I mean? Obviously, I must mean obviously, it's not just any curve. We need to ask what kind of curves we want to string through them. Clearly, I can't put a line through those 5 points. And less clearly, but something many of you may be familiar with, and that'll come up soon, is that we can definitely put a conic through those points. So what kind of, so the question we've implicitly put in there is, what kind of curves are we talking about? And the answer we've implicitly also said is we're talking about algebraic curves, the things we can talk about algebraically. I'm not saying, can I string y equals sine x? I'm not trying to do some clever, I should explicitly say, I want exact solutions. I'm not trying to, there are extremely interesting questions of fitting curves as approximately to match things. So the question is, roughly, still imprecisely, what's the simplest, I give you a bunch of points in the plane, in space, what's the simplest kind of curve that we can use to connect the dots? Okay, and I also want these points to be general points, or by which I mean generally chosen or randomly chosen points. Now, why am I asking that, or why am I specifying that? Well, it's just that the question is, first of all, much less well defined otherwise, because I could put, if I just said 5 points, well, maybe the 5 points are on a line. Maybe the 5 points are the same point. So the question, like the general question, is if I have 5 general points, randomly chosen points, there should be a single uniform answer, and then I can worry about special cases after that. But this is so I want to, whenever I say through a bunch of points, I want them to be general. And then where I really want to go is, at this point I drew them in the plane, and later I want them to be more generally in space, or in space of any number of dimensions. Okay, so let me try some small cases just so we can see what goes on, and we're going to be led to discover a lot of important concepts. And again, for many experts in the room in different fields, the concepts we're discovering are things that are well known because they're the concepts you're led to discover. But it's neat to see how they're forced upon us by asking very reasonable questions. So through any 2 points, we know we can find a line, and this is, I want to say it's from Euclid, but it's kind of an axiom, so I can't really say it's from Euclid. But and we also know that we can't fit a line through 3 generally chosen points. And this part of the discussion for now holds not just in the plane, but it's true if I have 2 points in space, there's a unique line through them. If I have 3 points in space, there's no line through them. And so if we want to generalize this, the first classical thing to do, a place which you would have maybe seen this, is if you have n points in the plane, and I'll give them coordinates, and let's say they have distinct x coordinates. Is there a function? A polynomial that sends xi to yi for each I, and if the polynomial is too small, the degree of the polynomial is too small, and the number of points is too big, you can't. And if the degree of the polynomial is really big and the number of points is small, you definitely can. And so in general, you can make, if your conditions are, once again, general, randomly chosen, then you can find a degree n-1 polynomial through n points in this way, and you can't find a polynomial of lower degree. And I should say that the thing about preparing this talk in the fall is that it ended up, the people who are not going to thank you are the people in my Math 120 class, because I put this question on my final exam, because it was very much on my mind. And I want to go through the thinking behind this, because we're going to see this grow up to be something interesting as well. Which is, okay, so you want to see if you can find a polynomial sending xi to yi. And so what this is you have these d+1 mystery coefficients you're trying to solve. So you have n equations that when you plug in xi and yi, you have n different equations. You have n equations and d+1 unknowns. And can you solve it? Well, if you have too many equations and not enough unknowns, and you get to name the equations, and your points are picked generally, then cheaply you can arrange for them to have no solution. So that explains, in this example, this is why if you have 3 points, you can't fit a line through them. This is the generalization of that. But then what happens when n is equal to d+1? Well, in this case, you have exactly the right number of equations and unknowns. And so maybe you can solve them, and you would even expect to be able to solve them if they're generally chosen equations. And to do that, you need to do linear algebra, which involves a certain determinant being non-zero. And that determinant is this Vandermonde determinant, which has only x's in it. And so in the course of, so the edge case is the crucial case, is a hard case, and we're led to interesting mathematics. We get this determinant, we get this matrix whose determinant is in fact non-zero. So the lesson that we should try, there are many lessons to draw. I feel like from Lagrange interpolation or from the Vandermonde matrix, there are lots and lots of lessons depending on what kind of lessons you want to get. But for example, we saw that some things are easy to show for cheap dimensional reasons. And showing that you can solve interpolation problems, that you can actually solve them, especially in the edge cases, then you're led to particularly interesting mathematics. You're led to, for example, discover the Vandermonde matrix. Okay, so at this point, we know that if we have 3 points in the plane, then you can fit a unique parabola through them. That's the degree 2 version of Lagrange interpolation. And then a better degree 2 version of interpolation would be the fact that if you have 5 points in the plane, then Pappus of Alexandria was well aware that you could fit a unique conic through them. And so what's a conic? Well, Pappus wouldn't say this, but so as you know, a conic is given by this equation in xy coordinates with 6 mystery coefficients. And the interesting thing is then how do you prove this? Well, at first you might think that, well, why can't you have 6 unknowns, so maybe 6 general points in the plane should let you should determine a conic, not 5. And the reason for that discrepancy is that, well, really there are 6 unknowns, but they don't really, there's only 5 degrees of freedom for the conic, because you could take the equation for a conic and double it, the equation, but you get the same conic. So the conics don't form a 6-dimensional family, or the 6, but they form a 5-dimensional family because any 2 conics are the same if one is a non-zero multiple of the other. And now we come to an excuse to talk about what Pappus of Alexandria would want us to talk about, which is projective space. So let me briefly discuss projective space, just because it's going to be so important. I want to make sure that you are that you're fluent with it if you haven't seen it before, or if not fluent, then at least you would have seen it. So the conics involved, so the different conics involve these 6 numbers A through F, and we said one conic would be the same as another conic if the coefficients were all, one was the scalar multiple of the other. So what we've described is real projective 5 space, where we take 6 numbers, not all 0, and this one 6 tuple is the same as another if one is a non-zero multiple of the other. And then the projective geometry comes up also not just in the space of conics, but in the conics themselves. And this is, we're definitely in Pappus's, in the land of Pappus now, which I guess was Egypt. So where instead of in R2, and this came up in Holly Krieger's talk for those who were here in the previous hour, where instead of writing the conic in xy coordinates, you homogenize in xyz coordinates, and you think of this as living inside some compactified version of R2. So there's just a reinterpretation or translation, which gives you numerous advantages, which in particular means that all smooth conics look the same. Okay, so let me describe this 5-dimensional family of conics in a different way. So we're trying to interpolate. We have 5 points. We're trying to draw a line through them. So let me just map a line through them, parameterized by t. And so I want a degree 2 image. So I'll take t and I'll send it to quadratic things. And I'm going to map it to P2. So I have 3 quadratics in a row, at squared plus bt plus c, all the way to gt squared plus ht plus I. And so I wrote it in some sort of, I sort of wrote it in projective coordinates, sort of not. So if you don't like projective coordinates, then you just can dehomogenize and you get this thing with fractions. And that's what I mean if you like that. Or if you prefer projective coordinates, then you could write it by sending the source, instead of being t, it's a point in P1, x comma y. And to translate them back and forth, you just replace t as y divided by x. And so in terms of projective coordinates, this is just a different point of view, a different formulation. It's nothing new. You're just sending x comma y to, and I'm write down 3 homogeneous quadratic polynomials. But either way you slice it, there are 9 mystery unknowns. There are 9 choices to make in describing what this map is. Okay, so let me see this. Okay, so here I have this family. I'll just choose one of the incarnations of writing it. So these are parameterized degree 2 things. And if I said how many dimensions is this family, well, I have 9 unknowns, A, B, C, D, E, F, G, H, I. But you can see from the way I wrote it here or in the other ways I wrote it, that if you double all those 9 numbers, you would still get, because you're dividing them, it's the same up to scaling. So really, secretly, there are 8 dimensions in play. But we're expecting to see 5, and we're not seeing 5. So where did the 5, what's the difference between the 8 and the 5? The difference is because we're mapping P1, we're mapping T in, and we're giving a parameterized version of the curve, whereas we just wanted the picture of the curve. So you have to forget the parameterization. You have to forget the parameterization of the source curve, and that turns out to be a 3-dimensional group. And that turns out to be 3-dimensional, and that explains your remaining 3 dimensions. So here you have 2 different ways of understanding conics. One is with like a single equation, and one is by mapping something in and have it be parameterized. Okay, so now that was degree 2, and that was Pappas, and that was over, I don't know, 20, over, I'm guessing it's, okay, there might be a historian in the room, but I can just make it up. It's a 2,952 years ago. Okay, so let's try degree 3 curves. Let's do cubics next. And so let's try to see how many points we can connect with cubics. So what does a cubic plane curve look like? And I'll write it in projective coordinates. And if you don't like projective coordinates, again, pretend z is equal to 1. So that's what all cubics look like this then. And if you count, there are 10 coefficients to name. So how many cubics are there? What's the dimension of the family of them? Well, it looks like there's 10, and then but we know that there's a multiply it by a non-zero scalar, you get the same cubic. So it's 9-dimensional, a projective 9 space of cubics. So that's our first answer. But I want to think about it by parameterizing it, so I want to give the second answer, just as I did with conics. And so we do the same thing. We send t to a bunch of degree 3, we write down 3 degree 3 polynomials. Or if you don't like that, you could divide the first and the second by the third. And let me count dimensions again, so I should get the same answer. So how many mystery coefficients do I have? How many coefficients do I pick? Well, I have A through L. I have 12 coefficients. But really, if I double them all, I get the same thing. So really, there's a spare dimension I should subtract. And I still need to subtract 3 for the choice of parameterization of the source curve of the P1. So I get 12 minus 1 minus 3, and I get 8. And I don't get 9. So I'm now getting, now I get a different answer. In the case of cubics, I'm getting two different answers. Is it 9-dimensional or is it 8-dimensional? Actually, as an aside, I was talking with Grant Sanderson by coincidence. I didn't realize it was going to be about the same thing, about an idea he was working through, and I explained like a riddle I often give algebraic geometers. It's not really a riddle, it's a question, which is how do you show that there's a curve, provably, that's not a rational curve? And how do you explain it to someone while using as little technology as possible, without using as little fancy machinery as possible? So you don't need to take a year to define topology. And the great thing about it, if you ask different people, depending on your point of view, there are different ways to explain it. But it's interesting how everyone has a different sort of complication. And so I think the one I'm about to say has I like it because it feels very low tech, although there are hidden complications in it as well. So that's what's about to arise here. So what we basically should have shown is there's a 9-dimensional family of all cubics, and there's an 8-dimensional family of parameterizable cubics. So where's the contradiction? There is no contradiction. What we now know is that most plane cubics are not parameterizable, unlike conics. And again, like where's my argument not? How is that not a fantastic argument? Well, it wasn't very rigorous, and I didn't really define my words, and the devil is always in the details. But really, this is a proof that most cubics cannot be algebraically, or not parameterizable in the way that I'm describing. So let me try to make this more precise. And now I'm about to reveal my true colors, which is when I draw pictures, we've been talking about the real numbers, but over the complex numbers, things become really much clearer. So I'd like to talk about, do everything. I talked about the real numbers, but really nowhere, except from drawing pictures, did I use anything about the real numbers or any field, really. So let me do all this in the complex numbers. And then most cubics, it turns out, look like a donut. They have a hole in them. So x cubed plus y cubed equals z cubed has genus 1. Genus is the name for the number of holes. But if something's parameterizable, well, you're mapping P1, CP1, which is a sphere, it has no holes, and you're mapping it into somewhere else, and so it can't look like a donut. So there's some topological thing going on that's causing a problem, or that makes it look different. And what's going on is it forces that sphere is going to have to cross itself somewhere in the plane. Or if you want, what's special about a cubic that makes it parameterizable is that you need to squeeze part of the donut so it gets squeezed down so it really turns into something like a sphere touching itself or crossing itself. And that's so over the complex numbers, it becomes more visible. But what I said before was an absolutely true fact about real things. So to understand, so the nature about something over the real numbers not being parameterizable is somehow captured by what's going on in the complex numbers, even though in some sense I feel like it's like a very surprising thing. If you go over the real numbers, they're just like, like what does a cubic look like? It's just like it's like an S, it might look like that, or it might have two pieces. It's a very simple thing, and yet somehow what's going on in the complex numbers is what's distinguishing it. And I want to contrast this for those who saw Holly Krieger's lecture in the previous hour, not even contrasted, to say similarly, if you try to solve Diophantine problems, which are about rational solutions, which are a subset of the real solutions, magically what's going on with the complex numbers is telling you what's going on with the rational numbers. So this is part of this magic of, I don't know whether it's algebra, geometry, mathematics, analysis, how what's going on in one part of the subject somehow influences what's going on in a different part. Okay, so now, for that reason, I'd like to work over the complex numbers and not over the real numbers or any other field. And so it makes my life easier. And a neat thing is that you can make sense of the genus over any field. And I hope I've semi-convinced you of that, because even over the real numbers, the genus made sense. Because even over the real numbers, whether you could algebraically parameterize something, it still makes sense. And the only thing to keep in mind, and what I'm saying is that, a few things to keep in mind, is that, some things are better about the complex numbers, which is that really it always, almost the main thing boils down to the fact that every degree n polynomial has n roots. And the real numbers, you have to worry about things that I find very confusing, and I'd prefer not to. Or if I need to, I'll first think about the complex numbers and then worry about whether the roots are real or not. And the other thing is that the notion of dimension is slightly odd to picture, or maybe slightly even. That, to me, these pictures are curves. So these are complex curves, and I guess normal people will say Riemann surfaces or complex, but these are one-dimensional things, I would call, but they're complex one-dimensional things, not real one-dimensional things. And the advantage of using this language is then you use the same words in a field-agnostic way. And you can even talk about dimension over other fields, even though you can't draw pictures. So dimension makes sense, even though you can't draw a picture. Genus makes sense, even though you can't just count holes. And that's part of the magic, that you can define these things in ways that actually doesn't care about the field. Okay, so through 9 general points, in the plane, you can pass one plane cubic. That was a thing about just writing down a qubit. I forget what the coefficients are, but you can't pass it through 10 points. And genus, I wanted to mention, just because this number comes up, and whenever this number comes up in math, I get happy, that parameterizable cubics, in general, you can't pass them through 9 general points, but you can pass them through 8 general points. But it turns out that if you pick 8 general points, you can pass. There's a parameterizable cubic, but there's not just one, there are 12 of them. And that magic number 12 is always, like, whenever you hear 12, especially if you're in algebraic geometry, you know elliptic curves are in the background. And they are indeed, but I'm not going to tell you. Okay, great. So now let me go back to interpolation for plane curves. So what I said earlier is that, it turns out that in general degree, D, not just degree 3, the plane curves have genus D minus 1 times D minus 2 over 2. That's why degree 1 and 2 are very special. Degree 3 is still pretty special. And it turns out every genus in between is possible. And I want to, again, emphasize that our dumb dimension counts, or the not so dumb dimension counts, show that one could just say that among all degree 4 curves, only some of them are parameterizable and most are not. But the fact that there's a notion of genus says there are degrees of non-parameterizability, that a random quartic you write down is genus 3, even if you're thinking about the real numbers. But some of them, some special ones are genus 2, and even more special ones are genus 1, and super special ones are parameterizable. So I just want to emphasize that even if you think about the real numbers, these notions matter, and you can see this in the 19th century, and I think even possibly the 18th century literature, and I'm just making up my history anyway, so you don't really care. But you can really see it in the literature, except they didn't have the language for it, and they didn't realize what was fully going on, but they had words for it. Okay, so in general, if you know the degree and the genus, then once you fix how parameterizable you want them to be and what the degree is, then you can figure out how much you interpolate. You can figure out how many points you can pass them through. So if you tell me the degree and the genus, and you know what genuses are possible, what genera are possible from the previous slide, you can see how many points you can hit. And just I want to mention an aside of like all sorts of interesting mathematics that came from this. If it seems like a random question, but the actual number tends not to be 1 unless you're lucky. So the 12 I mentioned a slide or two ago, that generalizes to any degree and to any genus, and that number has turned up in different parts of mathematics. There's a great paper of Zevran from 1989 by Caprasso and who's my academic older sister, and Joe Harris from '97, and many more. But it also connects to things in many different fields. So I heard from Federico Ardila. I don't know if there are any. I would say we're in San Francisco. So are there San Francisco State people here? Anyone who's been from who's spent time there? If there are people from San Francisco, so Federico Ardila, who's a combinatorialist, has a great paper where there's a combinatorial, where it translates to some combinatorial question as well, which has an identical, provably same beautiful answer. And these questions also relate to something in Gromov-Witten theory, which are invariants that came out of at least ideas motivated by string theory. And I don't know whether you call that physics or not, but it's at least beautiful mathematics, even if it's not real. Okay, so let me now let's go to higher dimension, and this is where so that was a setup to where things are really well understood, and now we're going to go to where things behave more strangely. So once you're in a higher dimensional space, 3 space or higher, then you still have the notion of a genus, of course, because that's just the number of holes the curve itself has, and it turns out you do have a notion of degree, which you could talk about in terms of its homology class, or the way to say it. In the plane, it's just the degree of an equation, but it's harder to say what the degree of something of higher codimension is. But one way to say it is you have a curve inside projective space, you slice it with a hyperplane, count the points, that's the degree. But the way I think about it is these are 2 measures of the complexity of a curve in space. One measure is kind of like the degree of the equation of the degree is like the degree of the equation in some sense, and the genus is the complexity of how well you can parameterize it. So you have these measures of the complexity of curves in projective space, and then you can ask the question now, how many points can you string such a curve through inside projective space? And already implicit in this question, in the way we've been thinking about it, is it's not just I don't even know how to, I can't help look at this problem without realizing having this next concept, which is that we have in our mind a space of such curves. In the same way that we had, there's a space of conics, that was a P5, a space of cubics, there's a space of parameterizable cubics. The notion of a moduli space is seen as a very technical notion, yet it's something that you intuitively already understand, I think. So the idea is that there is a space of such a curve, of such curves inside of degree D, genus G curves in projective space, that there should be a notion of such a space. And the first approximation, the most important thing in this interpolation question is, what is the dimension of the space? And just to repeat examples from before, if we're talking about cubics that are parameterizable, there's an 8-dimensional family. And the reason the interpolation problem was that we can pass them through 8 points is that there's an 8-dimensional family of parameterizable cubics. And if you imagine families of curves moving on the plane, and they vary a bit, it should be somehow in codimension 1. It should be like codimension 1 rareness that it passed through this point, for example. If the curves move around in codimension 1, if they're parameterized by t, it should be like finally, there should be distinct values of t for which it passes through that point. So that's why if it's an 8-dimensional space, you can impose 8-point conditions and not 9. So in higher dimension, if you have curves in higher dimensional space, then you could ask, okay, then we have our question, which is we have curves of fixed degree in genus, and then I can ask how many, what's the dimension of this space, or how many points can I pass them through? And here I could probably just end the lecture because we do not understand, this thing is a horrible, it's in fact it's a provably horrible space in that there are many, many different families. We don't know how they can be all sorts of different dimensions. And for example, we do not know definitively if you give for all genera degree in projective spaces, I can't tell you if there's a genus G degree D curve in that projective space, sitting in that projective space. We actually do not even know if they exist or not. In some sense, the question is there's nowhere to even begin. And now I should say, before I get back to the story of interpolation, I'm going to say, really, the story I'm describing, it starts with interpolation. But really, in algebraic geometry, the impetus comes from kind of a different direction, which is, the real reason this is interesting is that we want to understand curves. We want to understand Riemann surfaces. And how do you understand abstract Riemann surfaces or abstract curves? In fact, we didn't even have a notion of an abstract curve, or we didn't know what an abstract manifold was until around 1900. And now my history actually is a bit more correct and not just made up, because the notion of an abstract thing is very confusing and hard to explain, and you forget how hard it is if you haven't, because if it's been a long time since you you learned about it yourself, and it's hard until you realize it's hard when you try to explain it to someone. And so the way you understand an abstract thing is you embed it somewhere, and so the study of curves is fundamentally the same, or at least you can't say one without the other, with this understanding curves sitting inside space. And so this is something about how whenever you want to understand intrinsic geometry and extrinsic geometry, there's this interplay between those two things. And that's why we want to understand curves in space. Okay, so let me go back a step. And I said that if I tell you the degree in the genus, and I ask you about those curves in projective space, and I said there's like really crazy stuff can happen. But here's the thing which makes things better, which is all the bad stuff, all these crazy families, all the curves involved are special curves in some way, except for one family. All the badly behaved stuff they're all special. For example, this is a metaphor. I don't know if this is going to be sort of helpful, but if you have genus 1 curves, you may know they're parameterized by a J invariant. The analog is like saying, well, all the bad things there's only finitely many J invariants that are bad, but for most J invariants, it's fine. So what I want to say is that if you tell me what kind of curves you want to discuss, what degree, what genus, their complexity, and where they're living, then there's exactly one family that has the random curve, a general curve, not a special kind of curve. So there is exactly one family, and I know the family's dimension. Actually, what I wrote is slightly a lie, which is, what if this dimension is negative? So the real statement is that if this dimension is 0 or better, then there's exactly one family and it's that dimension. And if it's negative, then there's no such family. So this is this theorem, the Brill-Noether theorem. This is the driving. This has driven the subject for, I guess, maybe a century. I don't know if it's a century to a century and a half. So the ones we care about, the questions, the curves in space we care about, are these Brill-Noether families of curves, the ones that include general curves. And now we have the interpolation question, finally, which is how many points can I string one of these curves through? And now I know what kind of curves I'm talking about. These are the curves, and so I've got these families. I know the dimension there. I know the dimension of the family, and already I'm in a great position to roughly tell you the answer, because the condition of now you can check your geometric intuition. If you had families of curves in 3 space. Mostly they won't, what are the odds that they'll pass through this point? Well, they probably don't. It's like a codimension 2 condition for a curve, for a family of curves. It should be, if you have a family of curves in codimension 2, will they pass through this point? And in general, in projective R space, it's a codimension R-1 condition for it to pass through a fixed point. And so the blunt dimension argument is that you have no hope of interpolating more. So you have the dimension of the family, which I told you what it is, which is this big theorem. How many points can you hope to pass it through? We'll just divide by R-1, and you shouldn't be able to pass through more than those points. And that's the statement that should be true. It's telling you roughly how many points can you hit by these. Well, I guess it literally means you have curves moving around in projective space, and you're basically saying how flexible, how wiggly are they inside space. And now comes the only thing better than a conjecture is a conjecture that's false in an interesting way. And so this conjecture is false, and let me tell you how it's false. And so let me give an example. So the example will be in 3-dimensional space. There are no problems in the plane, because I've talked about the plane. So the problem's in 3-dimensional space. So it's genus 2, curves with 2 holes, degree 5 curves, and they live in a family, and I'm just going to copy the equation from the previous page, in a 20-dimensional family. And the condition of passing through a point costs you 2 dimensions each time. So it's got a fighting chance of being able to string one of these guys through 10 randomly chosen points. And they can't, and the reason they can't is interesting, because it turns out that curves, any such curve like that, has to lie on a hyperboloid, on a quadric surface. And so there's a picture of the quadric surface from Wikipedia, but when I say on a quadric surface, I don't mean a nice one with nice coordinates. It might be tilted it might be a weird ellipsoid, something like that. And so the thing about quadratic surfaces is there are, well, what is a quadratic surface? I can write down an equation for it. The equations look like what I wrote down. If you don't like projecting coordinates, pretend z is 1, or no, w is 1, I guess. It's because x, y, and z are what people like. And the quadrics, there are like 10 coefficients to name. So there's a 9-dimensional family of hyperboloids of 1 or 2 sheets. There's a 9-dimensional family of quadrics. And so that means that they can pass through at most 9 points because, for basically the same reason that a conic can pass through at most 5 points. So, these quadratic surfaces can pass through at most 9 points. And that means that no quadratic surface can also, well, that doesn't mean, but more importantly for us, no quadratic surface can pass through 10 general points. If you pick 10 general points in space, there's no quadratic surface that can pass through those 10. And that means that there's no genus 2 degree 5 curve that can pass through those 10 points, because it would have to lie on a quadratic surface, which also would pass through those 10 points, and that's impossible. So the fault is the curve is moving around a lot, but it's kind of moving around in this ambient family of surfaces. There's like a hidden structure, and I feel like mathematics is all about finding and teasing out hidden structures that were not obviously there before. And then they tell you something and tell you where to look for more things like that. And it turns out that there are 3 other counterexamples, and I can tell you the numerology, but these are at least 2 of these 3 examples. These all are after the fact. You look at them, and if you know what to listen for, there are clues that something funny is going on in each of these examples. But also in each of these examples, the reason for the thing going wrong is there's something like the hyperboloid with 1 sheet. There's a surface, a hidden surface in the picture that is there. And actually, it's not just a random crazy surface, it's a parameterizable surface. There's a notion of parameterizable in higher dimension as well. There's some hidden structure that's causing it. So what's the interpolation conjecture? The better version is that, well, of course, what you do as a mathematician is if you have some counterexamples, your new conjecture is that, except for the counterexamples, this must still be true. But it's really the wrong. And of course that's like morally somewhat unethical. But sometimes it works. But you have to figure out what it is you're trying to prove and what morally is going on. And in some sense, there is a 5th counterexample, which I believe came through in the proof. I don't know if it predates Larson and Vogt or whether it came up in their. I would imagine more likely it came up in their argument, because it's the sort of thing you only understand when you start to think really cleanly about the problem, which is you have a family that really is able to hit the points you want, but yet somehow the points, it's again, fairly small numbers, degree 6, genus 2, and 4-dimensional space. Not the thing you run into on a street corner, but at least not something, well, in San Francisco you run into strange things on street corners, and so maybe one does run into it, and then you actually do, so there it's a family of curves that moves in a certain dimensional family, and it wiggles around a lot, but not as much as somehow it's constrained in a way that you do not expect, and I'm deliberately not giving, it takes a few minutes to describe what secretly is going on, but there always is an explanation. Okay, so let me spend the last part saying something about how one proves such a thing and shows that curves move about in space in the way that they are supposed to. And now I'm going to describe things which is, it's not so much lying as telling you things that predate the chunks of their proof. So these are general themes of how you do such a thing, and the best way to do it is to do it in an example that we already know, which is how I always understand proofs the best, which is how do you know that there is a conic? The tricky question is, if I give you 5 general points, how do you know there's a conic through 5 general points in P2? And you could do specific algebra, or you could try to say something more general. And the sneaky idea, but a very old idea, is that you don't do 5 generally randomly chosen points. You pick 5 special points, and the points I will pick will be 5 points where 3 of them happen to be on a line. And in that case, it's really easy to see that there's a conic through those 5 points, And that's because I can just draw one line through those 3 points. And then I've got 2 left over, and I draw a line through the other one, and the union of those 2 should reasonably be a conic. So I've got my conic, but I did not answer my question. And so how do I answer my question? And why didn't, you could have said, well, why didn't I just put all 5 on a line? Well, it's going to make the next thing not work. So if I take my 3 points are on a line and 2 are not on a line, and that's my conic, and it's blue. But now think about, I didn't want my 5 points to be special, I wanted them to be general. So let me make them less special, and I will take one of those 5 points and move it off the line. But it's now going to try to carry the conic with it. And if it can carry the conic with it, then I've got a conic through 5 general points. And the reason this is somehow easier, because I'm not actually constructing the conic, I'm starting with something I had previously constructed, and I'm just asking if it can move, if it's like flexible in that direction. And so the question, and as you can see, I'm not a good artist either. But the question is, if you take one of those points, can you have the conic still pass through the other 4 and also pass through this moving one? And so how do you make this precise? Well, you need to know what's going on kind of near that that curve with the singularity, that nodal curve. You need to know what's going on in this tubular neighborhood. And now I'm going to feel comfortable using fancier terms because I only have a few minutes left, but I still want to use them in some intuitive way so you can see the kinds of thought, the kinds of thinking that goes into it. There's some analog of like the normal bundle to the curve you have, and then some weird stuff is happening near the point where the curve isn't smooth. So a step to their argument, but again, this partly predates them, and their cleverness is what they do with this as well, is understanding the normal bundles to these curves. So if you have a curve in space, and maybe it's going to become, well, in their case, now they start to be clever and it becomes extreme, they're no longer nice smooth curves in this space. You want to understand what's going on near that, and it would really help if you could say that, well, I know the curve and I know something about it, and the normal bundle is probably some randomly chosen randomly behaving bundle with these properties. Generally behaved bundle with these properties. And I mention this just because there's something which is, even if you care about the real numbers and the complex numbers, and that's the argument which you're going to be making, there's something, this is like a way in which things in other characteristics give you clues that something funny is going on. And this example, which kind of is somewhat jaw-dropping in that it was unexpected when they described it, and then once they see it, you can explain why it's true. But I think I wouldn't. There's no reason to have guessed it if you didn't realize that you should be looking for it. Which is that, in fact, even for genus 0 curves, parameterizable curves in projective space, the normal bundle does not behave in a random way, but only in characteristic 2, in the fields where 2 equals 0. So, okay, so you might think, who cares? I don't live in a characteristic 2 world, but it means that your proof has to either somewhere in it say, and here's why the characteristic is not, here's where we use that 2 is 0, or you have to cleverly avoid this pathology. So somehow the fact that this problem is there suggests how the proof has to go. And depending on your point of view, this can be seen as some sort of 6th exception. Okay, so let me just say something. Now I get to say something general and vaguely claim that it's because I'm running out of time. Although I'll be, as you'll see, because the slides are prepared in advance, that this is not actually that I'm just making this up. Because I designed this to run out of time exactly right at this point, which is that the nature of what they did is as follows, which is it's a combination of 2 things. So let me say something general, then I'll talk. Let me describe the argument, the flavor of the argument, and then I'll give you this 1-paragraph summary, which is how do you solve the problem for arbitrary genus, arbitrary degree, arbitrary projective space? Well, obviously, one's using induction of some sort, because you're not, and so, well, what's the induction you're going to use? How are you going to reduce the question to something with smaller genus, smaller degree, smaller projective space? Just like with the conic, you turn the question about the conic into questions about how many lines are there through 2 points, and then questions about how you deform, and then how you deform out of that situation. So there's the deformation theory problem, and there's a very judicious turning of your problem and making your deformation, figuring out how to break it into 2 pieces that are things you've seen before, that are simpler, and that for which your result also holds. And what makes it more complicated is there are counterexamples it's not that the general statement is true. There are 4, 5, or 6 counterexamples, depending on how you look at it. So you have to somehow get from there to a base case, and you have to sort of, it's like, I think of like skiing, and they're like trees you have to avoid, and what everyone had done up until this point. I think what I'm saying so far, someone around 1940 would have absolutely bought and said, sure, I tried that. And then they hit the tree, because there's way too many trees to hit. And so you have to judiciously figure out your path, miss every single tree, and the problem is the closer and closer you get to the base case, the denser the trees are. So maybe there is this feeling in mathematics, like when you like things are easy, and some sorts of arguments are easy in high dimension because you have more flexibility somehow to do things. And as you get closer and closer to dimension 4, suddenly your wiggle room is reduced, and you have to be really, really careful. And so that's why in the nature of these sort of arguments, things start to get more case by case, ad hoc, and painful the closer you get to the base case. So they had to figure out the strategy. They had to solve a more general problem, because there's no direct way in. You have to have a more general set of things you're inducting on, figure out that strategy that would actually work. And there's like the field is littered with failed attempts to find your way through the trees and then actually make it work. And so in some sense, like the assault is something which I think should not, the thing that was attempted, it was clear what one would hope to do. It's just that people had failed before, and so it was really in the execution, not in the strategy that had finesse and delicacy. But it also had. I also appreciate the fact that, as well as needing fancy abstract machinery, because you need moduli spaces and to understand deformation theory, but there's also roll up your sleeves and like really, at some point, like some people are infatuated with big machines, and other people are terrified of them. And it's better to be neither infatuated nor terrified. You use them, sometimes you're willing to get on a train and go somewhere, and other times you have to, like, your car breaks down and you have to get down and like fix what's wrong with it. And so in the course of this, there's both the very general structure, and there's also some code that's needed to make absolutely sure that no edge cases aren't missed by mistake, because it's so easy to make a mistake when you in a complicated induction. So the flavor is very satisfactory. So I hope I've given you some sort of tour of the ideas behind their proof and what motivated them to do this, and the kinds of questions are the things that people have been thinking about for 2,000, or actually the world was created 3,000 years ago, as I recently learned on a street corner of San Francisco. But basically, since that time, this question of putting curves through points and understanding how to fit through curves through points and naturally leads us to this question, a more and more refined version of this question. But now this question is absolutely completely settled thanks to Eric and Isabel. So thank you very much for your time.
Thanks for that wonderful tour. We have time for a couple of questions. There's a mic there if anybody wants to ask something. Robin.
Okay. Thanks, Ravi. I wonder if you've is this mic working?
It is now. Stand close to it.
What? That's good. Okay, closer. Yeah. You've been dealing with Brill-Noether general curves. So I wonder if you consider the case in projective 3 space where you fix the degree in genus but consider all possible curves. This was the subject of the PhD thesis of Daniel Perrin in Paris a number of years ago, and I wonder if there's further progress on that subject.
So I don't know if much that improves on that. I mean, that seems to be the hardest. I feel like the question of curves in 3 space seems like it remains the hardest, the single hardest part of curve theory. Is that correct? I mean, you would know as well as I would. This is actually, this is Robin Hartshorn who's asking the question. So this is.
Okay, thank you.
And there's a question over there.
Oh, hey. Oh, gosh. Okay, I should not be so close. Thanks for the talk. So I have kind of a naive question. So you said like this question was essentially resolve this interpolation problem for this like Brill-Noether curve. So are there any natural generalizations, like say, could you ask this question for whatever Brill-Noether surfaces are? Like, I'm not sure that's really a well-defined question, but.
So I would say you could ask similar questions for surfaces, especially certain parameterizable surfaces. I think the question would be very natural. But these are also related to other questions that remain completely open or very interesting in curve theory that are currently very active. This project is not in isolation. I think there are a couple of other major conjectures that were related to it that were resolved that this fits in the context of.
All right, cool, thank you.
And one more over here.
He actually asked my question, so.
Okay. Well, thanks to all the speakers for great talks today. Come back next year.